Hey, welcome to The Explainer. Today we're diving deep into the two secret worlds that are running your computer right now, user mode and kernel mode. You see, there's this invisible barrier at the very heart of your operating system, and once you understand it, everything starts to make sense, from why your favorite game crashing doesn't take down your whole PC to why your computer might not be as fast as you think it is.
So let's just start with a kind of crazy question. What if I told you that your computer, right now, might be running up to 30% slower than it's physically capable of? It's a huge number, right? And the reason for it? Well, it's all tied up in this constant battle to protect the very core of your system.
And the culprits for that slowdown? You might remember these names: Spectre and Meltdown. These were some really nasty security flaws that targeted the system's core so directly that the only way to fix them was to roll out patches that, actually slowed our computers down. It was a huge trade-off between security and raw performance, and that's the exact challenge we are unpacking today.
So here's our game plan. We're going to start by exploring your computer's two worlds using a really simple analogy. Then we'll see exactly how they talk to each other across a secure border. From there, we'll look at what happens when that core fails, how hackers try to break in, and finally, we'll see the ultimate balancing act that makes this whole thing work.
All right, to really get a handle on this, let's use an analogy. I want you to imagine your computer's operating system isn't a bunch of code, but a huge, bustling city. And just like any city, it has public areas where anyone can go, and then it has restricted areas. And that's the key to everything.
So first up, we have user mode. Think of this as the public part of our city. It's the parks, the streets, the cafes. This is where all your applications live. Your web browser, your music player, your games. They're all running here in a safe, sandboxed environment. Which is awesome, because if one app crashes, who cares? The rest of the city just keeps on running. But then, you've got kernel mode. This is the complete opposite. This is the high security control center for the entire city. We're talking the power grid, the water treatment plant, the air traffic control tower. This is where the operating system's core lives and talks directly to the physical hardware. And if something goes wrong in here, it's not a small problem. It's a citywide blackout.
So you can see this huge divide, right? Over in user mode, the public city, everything is about safety and isolation. One app crashing is just a local problem, no big deal. But kernel mode, the control center, is all about raw, unfiltered power and direct hardware access. It's super efficient, but also incredibly dangerous, because one little mistake in there is catastrophic for the whole system.
Okay, this brings up a really important question. If all your apps are stuck out in the safe public city, how do they ever do anything useful, like save a file to your hard drive or send data over your Wi-Fi card? Well, they need a safe and official way to talk to the control center. Think of it like a secure border crossing.
And the way this communication happens is through something called a system call. It's exactly what it sounds like. It's a formal, highly controlled request from an app in user mode, politely asking the kernel to do some heavy lifting for it, to perform a privileged task it isn't allowed to do on its own. Let's walk through it. Say your word processor in user mode needs to save your document. It can't touch the hard drive directly, so it makes a system call. This triggers a special kind of interrupt, kind of like ringing a doorbell to the kernel. Instantly, the CPU flips this little switch called a mode bit from 1 for user to 0 for kernel. Boom! It now has a temporary pass to the control center. The kernel takes over, safely executes the file-saving request, and when it's done, it flips the mode bit right back to 1. Control is then handed seamlessly back to your word processor. This little border crossing dance happens thousands of times a second, and you never even notice it.
And going back to our city analogy, it's just like that. As Dave's Garage puts it, you can just think of a system call as a formal request to the city's control room. The application, our citizen, never gets to go inside. It just fills out the paperwork, hands it to the staff, the kernel, and the staff takes care of the rest behind closed doors.
Okay, this table really lays out the power dynamic perfectly. On the left, you've got kernel mode. It's the master, the privileged one. Its mode bit is 0, giving it access to literally all the hardware and memory. But on the right, user mode is the slave. Its mode bit is 1, and it's stuck in its own little memory sandbox. But just look at that bottom row. Impact of a crash. That is the most important difference of all. A screw-up in user mode is contained. A screw-up in kernel mode is game over.
And that leads us perfectly into our next section. What actually happens when things go wrong in that super powerful, super privileged kernel mode? This is all about system stability. And one of the biggest sources of risk here is probably not what you'd expect. It's drivers. Yep, those little bits of software that make your graphics card, your printer, or your Wi-Fi work, they need direct access to the hardware.
which means they pretty much always have to run in the powerful and very risky kernel mode.
So what happens if you have a buggy driver and it misbehaves? It causes a fatal error deep inside the kernel that the system just can't recover from. On a Windows machine, this is when you get the infamous blue screen of death. On Linux, it's called a kernel panic. They might look different, but they mean the exact same thing. The control center has failed.
When you see one of those screens, the computer is basically throwing its hands up and waving a white flag. It's saying, look, something has gone haywire in the control room. I can't guarantee anything is safe anymore, so I have to shut everything down. It's a total citywide blackout.
So we've seen what happens with accidental failures. But now let's shift gears and talk about intentional ones. What happens when someone, a hacker, wants to break into the control room to cause chaos on purpose? This is where we get into security.
A perfect and, frankly, terrifying real-world example of this is the Stuxnet worm. This was an incredibly sophisticated piece of malware that was specifically designed to get kernel-level access so it could physically destroy industrial equipment.
Once Stuxnet got into kernel mode, it was basically a ghost in the machine with godlike powers. It could make its own files completely invisible, so you'd never even know it was there. It could intercept and change fundamental system commands. It could lie to your antivirus software and tell it everything was fine. It had total control.
Of course, modern operating systems have really beefed up their defenses. Windows now has something called Kernel Patch Protection, or Patch Guard, and the city analogy is perfect here. It's like having armed guards at every door to the control room, checking IDs and making sure only authorized code gets inside. Linux takes a slightly different approach with Linux Security Modules, which is this really flexible framework for creating super tight rules about who can access what part of the kernel.
So let's just step back for a second and look at the big picture here. With all these risks, with blue screens of death and hackers and Stuxnet, why on earth have operating systems been built this way for decades? Well, it all comes down to a fundamental balancing act.
And this is the core trade-off. On one side, you have kernel mode. It gives you incredible power, incredible speed, direct access to everything, but it comes with a very high risk. On the other side, you have user mode. It gives you safety, isolation, stability, but it's very limited by design. The entire architecture of your operating system is a delicate compromise between these two extremes.
All right, so what are the big takeaways here? First, your computer is always living in two worlds, a safe user mode for your apps and an all-powerful kernel mode for the OS core. Second, system calls are the secure, controlled bridge that lets them talk to each other. And third, this entire design is one giant, delicate balance between power, stability, and security. And you know, modern things like virtualization are adding even more layers of protection on top of this.
And that leaves us with one final thought to chew on. This dual-mode design has been the bedrock of computing for decades. But as our world changes, as security threats get more complex and our demand for performance goes through the roof, you have to wonder, is this old design still the best way forward? Or is it time for a completely new balance between power and safety?